In this lecture, I am going to present what is plastic hinge, what is plastic moment capacity, and what is shape factor, and also how to find out the shape factor of different sections. Then I would like to solve two problems. One problem that is on the symmetrical section, and in other problem that is unsymmetrical section. In these two problems, I will find out the shape factor of the section. Then coming to the shape factor. So before going to the shape factor, I would like to explain what is plastic hinge and what is plastic moment capacity. What is plastic hinge? Plastic hinge is a section at which all the fibers yield, and hence for any further load, rotation takes place at the section without resisting any additional moment. Then what is plastic moment capacity? Plastic moment capacity of a section may be defined as the moment which makes all the fibers at that section to yield and thereby form a plastic hinge. Then what is yield moment, and how to find out the yield moment in the elastic theory? As we know, in the theory of pure bending, we know the relationship between the bending moment and the bending stress. The relation, that is m by I is equal to f by y is equal to E by R, where m is the bending moment and f is the bending stress, I is the moment of inertia, y is the most distant point from the neutral axis, and E is the modulus of elasticity, and R is the radius of curvature. So from this relation, here we get m is equal to f into I by y, f into I by y. M by I is equal to f by y, then m is equal to f into I by y. This I by y is called the section modulus, I by y. So then we can write the expression m is equal to f into z. Z is the section modulus, so this is equal to the moment of inertia divided by the most distant point from the neutral axis. Z is the modulus of section, is equal to I by y. I is the moment of inertia of the section and y is the most distant point from the neutral axis. Then defining the moment causing extreme fiber to yield as yield moment. When the extreme fiber starts to yield, and during that period, what is the moment? That moment is called the yield moment. So the yield moment is defined. This is equal to the yield stress into the section modulus. The yield moment My is equal to Fy into Z. Fy is the yield stress and Z is the section modulus. My is equal to Fy into Z. Then coming to the plastic moment, the plastic moment capacity of a section is denoted by MP. Then what is the plastic modulus of section? The plastic modulus of section, that you can denote by Zp, and is defined as the ratio of the plastic moment capacity to yield stress. So Zp, this is denoted by Zp, is equal to Mp by Fy, where Fy is the yield stress, Mp is the plastic moment. Then Mp is equal to Zp into Fy. The plastic moment capacity of the section is equal to the plastic modulus of the section and the yield stress. Mp is equal to Zp into Fy. Then we can find out what is the shape factor. The shape factor may be defined as the ratio of plastic moment capacity to the yield moment. So here we know what is the plastic moment capacity and what is the yield moment capacity. Yield moment is equal to Fy into Z, and the plastic moment capacity is equal to Mp is equal to Fy into Zp. Then we can find out what is the shape factor. The shape factor is equal to plastic moment divided by the yield moment. MP, this is Fy into Zp, and My, this is Fy into Z. This Fy and Fy cancel each other in numerator and denominator. Then the shape factor is equal to Zp divided by Z. This is also defined as the ratio of the plastic modulus section to section modulus. As the plastic moment is greater than the yield moment, so the shape factor value is always greater than unit. Then coming to the shape factor of different section. So first we will discuss the shape factor of the rectangular section. So let us take a rectangular section, this one, and the width of the rectangular section is B and the depth of the rectangular section is D. And this is the neutral axis, this is the neutral axis. In the case of rectangular section, the elastic neutral axis and the plastic neutral axis, that is passing through the midpoint of the section. Here you see, this is the stress diagram corresponding to the yield moment, and this is the stress diagram corresponding to the plastic moment. Here this is the D by 2 and this is D by 2. This is the yield stress at the extreme fiber in the elastic theory, and this is the yield stress throughout the section in the plastic theory. Let us take a beam. In the beam at the mid section, the compression is above neutral axis and the tension is below neutral axis. So this is under compression, this is under tension. So here the compressive force in the stress diagram, and this is the tensile force in the stress diagram, and this is the y1 distance that is from the plastic neutral axis. Here the plastic neutral axis and the elastic neutral axis both are same in this case. So here y1 is equal to D by 4 and y2 is equal to D by 4. So first find out what is the yield moment. We know in the rectangular section the yield moment is equal to Fy into Z. Yield moment is equal to Fy into Z, and Z is equal to I by Y. Z is equal to I by Y. Moment of inertia by most distant point from the neutral axis, the section modulus. Z is equal to I by Y, and this value is equal to 1 by 6 BD square. Because we know in the rectangular section the moment of inertia about the neutral axis is equal to B dq by 12, and the Y, the most distant point from the neutral axis, this is the Y. This is the Y distance. From this to this is the Y distance, and the Y is equal to this is D by 2. The Y distance is equal to D by 2, and where you will get the maximum yield stress. So Y is equal to D by 2. This is the most distant point from the neutral axis where you will get the maximum yield stress in the elastic theory. So here B dq by 12 divided by D by 2. So that will give the 1 by 6 BD square. So this is the section modulus of the rectangular section. So the yield moment My is equal to Fy into 1 by 6 BD square. Then find out what is the plastic moment capacity of the rectangular section. Plastic moment. Find out the plastic moment of the rectangular section. So in plastic moment, the A1 is the area under compression. This is the area under compression, and the A2 is the area under tension. Considering equilibrium of forces, here this is the compressive force and this is the tensile force. So Fc is equal to Ft, and Fc here the yield stress remain constant throughout the section. So what is the compressive force Fc? Fc is equal to Fy into this one A1, Fy into A1. Fc is equal to Fy into A1, and Ft is equal to A2 into Fy, A2 into Fy, A2 into, this is A2, area A2 into Fy, A2 into Fy. But in the case of plastic theory, the plastic neutral axis divides the area into two equal halves. In the plastic theory, the plastic neutral axis divides the area into two equal halves. So here A1 is equal to A2 is equal to A by 2. A1 is equal to A2 is equal to A by 2, where A is the total area of the section. Thus the plastic neutral axis divides the area into two equal halves. Hence in rectangular section it is at the mid depth. So in rectangular section, the plastic neutral axis that will pass through the mid depth of the section. The plastic moment capacity is the moment of resistance when the yield stress Fy at all the fibers. So the plastic moment that you can find out, this is equal to Fc into Y1 plus Ft into Y2. The plastic moment you can find out. So Fc into Y1 plus Ft into Y2. So you have to take the moment of these two forces about the plastic neutral axis. So that is the moment Fc into the distance Y1 plus Ft into the distance Y2. But we know the compressive force is equal to Fy into A1 and Y1, and the tensile force is equal to Fy into A2 into Y2. Then after taking the common Fy A by 2, here Y1 plus Y2. Then but we know in rectangular section the area is equal to BD, then here A by 2 BD by 2, and what is the Y1 distance and what is Y2 distance? So the Y1 distance is equal to this one, D by 4, because this is D by 2. So here from the plastic neutral axis to the compressive force, this distance is equal to Y1 is equal to D by 4. Here also from the plastic neutral axis to the tensile force, this is also the distance is D by 4, because this total distance is D by 2. Then after putting this Y1 and Y2, you get MP is equal to Fy into BD square by 4. This is the plastic moment of the rectangular section. Here you know what is the yield moment of the rectangular section. My is equal to Fy into BD square by 6. Then after knowing the plastic moment and yield moment, then you can find out what is the shape factor. So the shape factor is defined as the ratio of the plastic moment capacity to yield moment. This is equal to Fy BD square by 4 divided by Fy BD square by 6. Then this Fy cancel each other in numerator and denominator. Then BD square by 4 by BD square by 6, BD square cancel. Then this is equal to 6 by 4. So the shape factor is equal to 1.5. So in the rectangular section, the shape factor is 1.5. So this is greater than 1. Similarly, the shape factor of different section, that also you can find out. For circular section, when the radius of the circle is r and diameter is d, so the shape factor is equal to 1.698. Similarly, in the triangular section, the width of the triangular section is b and height of the triangular section is h. So the shape factor is 2.343. These two you can find out the shape factor of the circular section and triangular section. Similar way, as we obtain the shape factor for the rectangular section. Similarly, here the shape factor for symmetric I section. Here we will find out the shape factor for the symmetric I section. This is the I section and this is the flange, this is the wave, this is flange. This is two flange and this is the wave. The width of the flange is capital B and the depth of the I section is capital D. So here what you have to do, you have to find out the shape factor by considering this total. This is, you take one rectangle and this hollow portion, this is B by 2 and this is B by 2 and this portion is small d. So you have to take this hollow portion, this portion, you take the width is B and the depth is small d. So you take, this is one rectangular portion. From this larger rectangular, so you have to deduct the smaller rectangle. Then you will find out the shape factor. So what you have to do here? So you have to take for larger rectangle. So this is the F1C. This is the compressive force, and for the smaller rectangle, the hollow rectangle, for a hollow rectangle, so you take the compressive force F2C. So this is at a distance d by 4 from the plastic neutral axis, small d4, and the F1C is capital D4 from the plastic neutral axis. This is the centroidal distance of this compressive force F1C, and this is the centroidal distance of compressive force F2C. This is for the hollow rectangular portion, and this is for the larger rectangular portion. Similarly, in tension, so F1T, so this is for the large rectangular section, and F2T is for the hollow rectangular section. So this is also small d by 4, and this is capital D by 4. So this is the symmetric I section with the stress diagram corresponding to plastic moment. So here also you find out the yield moment, then you find out the plastic moment, then find out the shape factor. The shape factor is equal to plastic moment divided by the yield moment. The yield moment is equal to My is equal to Fy into I by Y max. I by Y max. Moment of inertia by the most distant point from the neutral axis. So what is the moment of inertia of this I section? What is the moment of inertia about the neutral axis, elastic neutral axis of this I section? So here you take, this is the capital B, small d. So the moment of inertia of this one is B dq by 12, capital B, capital D, q by 12. Then you have to deduct this portion, the moment of inertia of this portion. Here this is B by 2, this is B by 2, the total width of this hollow portion is small b, and the depth of this hollow portion is small d. So what is the moment of inertia of this hollow portion? Small b into small dq divided by 12. Then you can find out the moment of inertia of this I section. So this is equal to capital B, capital dq by 12 minus small b, small dq by 12. This is the moment of inertia. Then what is the most distant point from the neutral axis? Y max. So here Y max you have to take, this is the extreme fiber from the elastic neutral axis to extreme fiber. This distance is the most distant point from the neutral axis. So here you take capital D by 2. Y max is equal to capital D by 2. This is capital D by 2. Then you can find out the yield moment. My is equal to Fy B dq by 12 minus B dq by 12 divided by D by 2. Then My is equal to 1 by 6 Fy B dq minus B dq by D. This is the yield moment. Then find out the plastic moment. Similarly, for finding plastic moment, consider solid rectangle of size BD and negative area BD. Here also you have to consider solid rectangle BD and the negative area, the hollow area, you have to take small b into d, small p into d, negative area or small the hollow area. Then you can find out what is the plastic moment. MP is equal to F1C into d by 4, F1C into capital D by 4 plus F1T into capital D by 4 minus F2C into small d by 4 minus F2T into small d by 4. Here MP is equal to F1C into d by 4 plus F1T into d by 4 minus F2C into small d by 4 minus F2T into small d by 4. Then after putting the value F1C is equal to the area into the yield stress. F1C is equal to area, because here the yield stress is constant. So yield stress, and what is the area of this portion? What is the area of this portion? This solid, half of the solid rectangular portion above plastic neutral axis, B into D by 2. The area is B into D by 2 and the yield stress is Fy. So this is equal to F1C. F1C is equal to Fy into BD by 2. And what is the distance, the centroidal distance from the plastic neutral axis? D by 4. Similarly, F1T is equal to Fy into BD by 2 and this distance D by 4. Then for negative area or the hollow area, so what is the area? F2CG is also equal to small BD by 2 into Fy into D by 4, and this one F2t is equal to Fy into Bd by 2 into d by 4. So this is the plastic moment. Then after taking the common Fy, My is equal to Fy Bd by 2 into d by 4 plus Bd by 2 into d by 4 minus small Bd by 2 into d by 4 minus small Bd by 2 into d by 4. Then after simplification, the plastic moment is equal to Fy by 4 into capital Bd square minus small bd square. Then after getting the yield moment and plastic moment, then you can find out what is the shape factor. The shape factor is equal to plastic moment capacity by the yield moment capacity. The plastic moment you know Fy by 4 capital Bd square minus small bd square, and yield moment you know 1 by 6 Fy capital B dq minus small b dq divided by d. Then after simplification, the shape factor of the symmetrical I section is equal to S is equal to 1.5 bd square minus bd square into capital D divided by b dq capital B dq minus small b dq. This is the shape factor for the symmetrical I section. Then coming to how to find out the shape factor for diamond section. So this is the diamond section. So here this is two triangle. When we will join the two triangle, then that becomes the diamond. So here the diagonal, this is one diagonal, this is another diagonal. So this diagonal width is b, and the height of this triangle h, and height of this triangle is h. Height of this triangle is h. So here the plastic neutral axis divide the area into two equal halves, A1 and A2, and this is the stress diagram corresponding to the plastic moment. This is one triangle, this is another triangle. So here the center of the area A1 from the plastic neutral axis, this is h by 3. Similarly, the center of the area A2 from the plastic neutral axis is also y2 is equal to h by 3, and this is the compressive force and this is the tensile force. So here also you can find out what is the yield moment, then what is the plastic moment, then you can find out what is the shape factor. The yield moment that you can find out by taking the what is the relation, My is equal to Fy into I by Y max. This is the formula. My is equal to Fy into I by Y max. But first we have to find out what is the moment of inertia about this axis. About this axis, central axis, we have to find out the moment of inertia of this diamond section. How we will get the moment of inertia of this diamond section? So here we have to take two triangle, and we know how to find out the moment of inertia of the triangle from the base. So from the base, what is the moment of inertia of the triangle? This is 1 by 12 into bhq, 1 by 12 into base into height q. This is the moment of inertia of triangle about the base. So here in the case of diamond section, we have to find out the moment of inertia of this triangle about the base and the moment of inertia of this triangle about the base. So that becomes the moment of inertia of the diamond section. So here 1 by 12 into bhq, and for this 1 by 12 into bhq. So this is 2 into 1 by 12 into bhq. This is equal to 1 by 6 bhq. This is the moment of inertia of the diamond section. Then find out what is the yield moment. The yield moment My is equal to Fy into I by Y max. So here you got I is equal to 1 by 6 bhq, and Y max is equal to the most distant point from the neutral axis. So here from this to this is the elastic neutral axis in the case of yield moment. So from this to this is the most distant point from the neutral axis. This is Y max is equal to h. So here you put h I by this is I is equal to 1 by 6 bhq divided by h. Then the yield moment is equal to Fy into 1 by 6 bh square. But we know what is the area of the triangle, A1, and what is the area of the triangle A2. The area of the triangle A1 is equal to half into base into height, half into b into h. Similarly, A2 is also equal to half into b into h, and what is the centroidal distance of this area from the plastic neutral axis, and what is the centroidal distance of this area about the plastic neutral axis. So here this is h by 3 and here this is also h by 3. Then you can find out what is the plastic moment. The plastic moment is equal to mp, this is equal to fc into y1 plus ft into y2. So in the case of plastic analysis, so you have to take the moment of this compressive force plus the moment of this tensile force about the plastic neutral axis. So the plastic moment is equal to fc into y1 plus ft into y2. fc into y1 plus ft into y2. But we know the compressive force is equal to fy into a1. The compressive force is equal to yield stress into the area of this portion, and the tensile force is equal to fy into a2. fy into a2, and this is the centroidal distance of the compressive force and tensile force from the plastic neutral axis. So mp is equal to fy a1 y1 plus fy a2 y2. Then after putting the a1 and y1, so finally after simplification you get mp is equal to fy bh square by 3. Then after knowing the plastic moment and the yield moment, then you can find out what is the shape factor. The shape factor is equal to plastic moment divided by the yield moment. So plastic moment is equal to fy bh square by 3, and the yield moment, this is fy bh square by 6. Then after simplification, the value, the shape factor is equal to 2. For diamond section, the shape factor is equal to 2. Then coming to how to find out the shape factor for general section. These are the steps. Using these steps, so you can find out the shape factor for any section. First, determine the moment of inertia of the given section about the centroidal axis. This is the first step. Then determine the yield moment using the equation. This is the equation, my is equal to fy into I by y max. So using this equation you can find out the yield moment. Then locate plastic neutral axis, that is the axis which divides the area into two equal halves. So in the case of plastic analysis, the plastic neutral axis, that is divides the area into two equal halves. First you locate the plastic neutral axis by taking the area into two equal halves. Since the stress is equal to the yield stress at all fibers, the area multiplied by yield stress give the force in that area. The force that you can find out by multiply the yield stress with the corresponding area in the compression side or in the tension side. The yield stress into area is equal to the force. Then determine the moment of force in each simple figures in tension and compression about the plastic neutral axis separately. Then you have to find out the moment of all the forces in tension zone and in compression zone about the plastic neutral axis separately. Then the plastic moment can be determined using the equation mp is equal to summation of fy into ay. Fy is the yield stress and a is the area and y is the, that is y is equal to distance of centroid of each simple figure from plastic neutral axis. Then after knowing the yield moment and plastic moment, here you know the yield moment and here you know the plastic moment, then you can find out what is the shape factor for different sections. The shape factor is equal to mp divided by my, the plastic moment divided by the yield moment. Then coming to the first problem, calculate the shape factor of the I section shown in figure. If the value of the yield stress is 250 Newton by mm square, find the plastic moment capacity of the section. So here first you have to find out the plastic moment capacity, then you have to find out what is the shape factor. So this is the I section, this is the I section, and here the flange width is given 100 mm and the flange to flange, the top of the flange to bottom of the flange, the depth capital D is given to 50 mm. Then the thickness of the flange is given 10 mm, and the thickness of the wave is given 6 mm. This is 6 mm, and the depth of the wave is given, this is 250 minus 10 minus 10. The depth of the wave is 230 mm. From this to this, from this to this is 230 mm. So these are the data given. This is the stress diagram corresponding to the plastic moment. So here you take, this is one rectangle A1, and this is another rectangle A2, this is one rectangle A3, and this is another rectangle A4. You take 4 rectangles here. The top flange one rectangle, and this portion is take second rectangle, the bottom flange is third rectangle, and this portion is fourth rectangle. And this is the force in the top flange, and this is the force F2 for this area A2, and this is the force for the bottom flange, and F4 is the force in the area A4, and this is the distance. This is the distance y1, centroidal distance, that is the distance of the force F1 from the plastic neutral axis y1, and y2 the distance of the force F2 from the plastic neutral axis, and y3 the distance of the force F3 from the plastic neutral axis, and y4 the distance of the force F4 from the plastic neutral axis. First you find out the yield moment. So you know here, so the yield moment that you can find out by using the equation my is equal to Fy into I by Y max. So here we have to find out what is the moment of inertia and what is the most distant point from the neutral axis Y max. So what is the moment of inertia of this I section? So here you take this is the area, the flange area A1, and this area is A2, this area A3, and this area A4. So here you take the moment of inertia of this portion first about the elastic neutral axis. In the case of yield moment, you have to take the elastic neutral axis. So what is the moment of inertia of this rectangle about the elastic neutral axis? So you know that is the parallel axis theorem. From the parallel axis theorem, so you have to find out the moment of inertia about the own centroidal axis. Then you have to take the area into centroidal distance square. So here for this rectangle, so you know that is about the self centroidal axis. What is the moment of inertia? B dq by 12. B is your 100 and D is 10. 100 into 12, 10, 100 into 10 q by 12. And what is the area and the centroidal distance about the neutral axis? The area is 100 into 10, and about this axis, what is the distance? The centroidal distance of this area. So this is the total is 250. So here 125. You have to deduct here minus 5. So 125 minus 5, whole square. So the area is 100 into 10 into 125 minus 5 whole square. So this is the moment of inertia. This is the moment of inertia of the flange portion. This is the moment of inertia of the one flange. Similarly, this side also the moment of inertia is same. So you have to multiply it by 2. 2 into this. This is the moment of inertia of the two flange. Then you take this rectangle A2 and A4. So here what is the width of this A2? 6 mm. So here you have to take the total. This is for this portion, for the middle portion. Here the neutral axis is passing through the CG of this area. So here you take the moment of inertia of this total rectangle, total wave portion about the neutral axis, 6 into this area. This is 250 minus 10, this is minus 10. 250 minus 20, this is 230. 6 into 230 q by 12. 6 into 230 q by 12. This is the moment of inertia of the wave portion. This is the wave portion. Directly you can find out, and the centroidal distance here from the, this is equal to 0. because the CG of this rectangle, this is your coinciding. So here the centroidal is equal to CG distance is equal to 0. So this is the moment of inertia 34900,167 mm/. Then you can find out what is the yield moment. My is equal to Fy into I by y max. So Fy is given 250 Newton by mm square, and y max the most distant point from the neutral axis. The most distant point from the neutral axis, this is your 125 mm. This total is 250, and the half of this depth is 125 mm. So this is 125. Then after putting this one, MO is equal to 6980,0333 Newton mm. Then find out the plastic moment. The axis at mid depth is symmetric axis, and the plastic neutral axis also same as the neutral axis. In this case, as this is the symmetrical section, here both the elastic neutral axis and plastic neutral axis both are in the same line. So here, because in plastic neutral axis, the area, the neutral axis divide the area into two equal halves. That is the compression area is equal to tension area. So here for A1, this is the force Y1, and for A2, this is the force Y2, for A4, Y4, and for A3, Y3. So here you take total, the plastic moment is equal to F1 Y1 plus F2 Y2 plus F3 Y3 plus F4 Y4. Then F1 is equal to Fy into A1, F2 is equal to Fy into A2, F3 is equal to Fy into A3, F4 is equal to Fy into F4. But we know Y1 is equal to Y3 is equal to 125 minus 5. Here Y1 is equal to this from plastic neutral axis to the center of this area A1. So this total is 125, and you have to take the minus 5 from the center of this rectangle to plastic neutral. This is 125 minus 5. Similarly, Y2 is equal to this center of this. So this is 250 minus this is 125 minus 10, 115 by 2. Y2 is equal to 115 by 2. Y1, Y3 is equal to 120, and Y2, Y4 is equal to 125 minus 10 by 2. And A1, A3 is equal to 100 into 10, and A2, A4 is equal to 6 into 125 minus 10. Then after putting the value, so the MP is equal to 79837500 Newton mm. Then the shape factor can be find out. Shape factor is equal to plastic moment divided by the yield moment. So 79837500 divided by 69800333 is equal to 1.144. So the shape factor of the I section, the shape factor of this section is equal to 1.144 answer. Then coming to the second problem, this is the unsymmetrical section. Determine the shape factor of the T section shown in figure. This is the T section, and you have to find out what is the shape factor of the T section. This is the unsymmetrical section. Here this is the plane, this is the wave. The flange width is given 120 mm, and the thickness of the flange is given 10 mm. Total depth of the T section is given 120 mm, and the thickness of the wave is given 10 mm. This is all about the dimension of the T section. So here also you have to find out the shape factor. So first you have to find out the yield moment, then you have to find out the plastic moment, then the ratio of the plastic moment to the yield moment. This is the shape factor. So for yield moment, first you have to find out the centroidal distance of this section from the top of the flange. So first for yield moment, so the elastic neutral axis from top fiber, you have to find out the elastic neutral axis from the top fiber, because here the elastic neutral axis and the plastic neutral axis both are not lies in the same line, both are different due to the unsymmetrical section. So here what you have to do? So first you have to find out the central distance above the top of the plane. So this you take yt. So you have to take this is the elastic neutral axis. This is the elastic neutral axis, but you don't know where the elastic neutral axis passing. So you have to take from this to this yt, and you have to find out this yt. So that you can find out. This is the straight diagram corresponding to the yield moment. This is the straight diagram. So first you have to find out the elastic neutral axis from the top fiber. From the top fiber you have to find out. So this you can find out yt is equal to this area into central distance of this area from the top fiber, and this area and the central distance of this area from the top fiber. This is a1 y1 plus a2 y2 divided by a1 plus a2. This is equal to the yt. So here yt is equal to 120 into 10 area into the central distance 5 of this area plus 110 into 10. This is the area of the wave, area of this portion, 110 into 10, and what is the central distance? 110 by 2 plus 10. 110 by 2 plus 10, that is 55 plus 10, divided by the area A1 plus A2, 120 into 10 plus 110 into 10. So this is equal to 33.70 mm. So this yt is equal to 33.70 mm. The elastic neutral axis passes at a distance 33.70 mm from the top fiber. This is the compression side and this is the tension side. Most distant point from the neutral axis, that is the y max, that you can find out by deducting this yt from the total depth of the T section. So y max is equal to 120 minus 33.70. Y max is equal to 120 minus 33.70. This is equal to 86.3 mm. So the yield moment that you can find out, my is equal to fy into I by y max. So here my is equal to fy, and here you know the moment of inertia I is equal to 3185253.7, and the y max is equal to 86.3. So the my is equal to fy this 3185253.7 divided by 86.3, this is equal to 36909.08 fy. This is the yield moment. Then find out the plastic moment. So this is the straight diagram corresponding to the plastic moment. So here this is the T section, and here first you assume this is the straight diagram. This is the straight diagram. This is the fy. This is constant throughout the section, and this is the 120, and the thickness of the flange is 10 mm. Total depth of the T section 120, and the thickness of the wave is 10 mm. Find out the plastic moment capacity. Assuming the plastic neutral axis lies in the flange. Here you don't know where the plastic neutral axis passes. Where the plastic neutral axis lies, that you don't know in this case. So what you have to do? So you have to assume the plastic neutral axis lies in the plane. The plastic neutral axis lies in the plane, because so the plastic neutral axis, that is divide the area into two equal halves. So here you see the flange. What is the area of the flange? 120 into 10. This is 1200 mm square. And what is the area of this wave? So this is 110 into 10, 1100 mm square. So here the area of the flange is greater than the area of the wave. So you have to assume the plastic neutral axis which is passing through the flange section. First you have to assume. Then you have to take the distance from the top fiber is yp. You have to take, this is top fiber and this is the plastic neutral axis, and this distance you have to take yp, and this yp that you have to find out. So its distance from the top fiber yp. So how you will find out this yp? Because here you see what is the area of this portion. The compressive area is equal to the tensile area, tension area. Area of the tension is equal to the area of the compression side. So here you have to take, this is A1, this is the area you have to find out. So this distance is yp, and what is the flange width? 120. 120 into yp is equal to a by 2. Yp into 120 is equal to a by 2, because the plastic neutral axis, which divide the area into two equal halves. So this area, the one half is your yp into 120, and the other half that you don't know. So what you have to take, yp into 120 is equal to a by 2, total area by 2, total area by 2. So total area is equal to 120 into 10 plus 110 into 10 divided by 2. This is the total area divided by 2. So here you got the yp value is 9.583 mm. So this is less than 10 mm. This is less than 10 mm. So the plastic neutral axis is passing through the flange of the T section, and this yp value you got here 9.583 mm. Hence the assumption is correct. Then find out what is the area under compression. So here you take this portion above plastic neutral axis, this area you take A1, and just below plastic neutral axis and in the flange portion this area take A2, and the web area you take A3. So for the above plastic neutral axis, the force you take compressive force, this is F1, and this distance is Y1, and for the below plastic neutral axis and within the flange section, so here the force you take F2, and the centroidal distance you take Y2, and in this wave portion, so the area is A3, and here the force you take F3, and the centroidal distance from the plastic neutral axis take Y3. So then you can find out what is the plastic moment. The plastic moment is equal to F1 into Y1 plus F2 into Y2 plus F3 into Y3. So this is the area under compression, A1 120 into 9.583. This is area under compression. This is A1. This is 120 into 9.583 area at A1. Then A2 is equal to this is total is 10, and this portion is 9.583. So this thickness into 120. So here A2 is equal to 120 into 10 minus 9.583. Similarly A3, this is the area A3. So A3 is equal to 110 into 10. A3 is equal to 110 into 10. 110 into 10. Similarly find out Y1. So here Y1 is equal to this, the total thickness here is your 9.583 divided by 2. Y1 is equal to 9.583 by 2. Similarly this one Y2. So Y2 is equal to, here this thickness is 10 minus 9.583 and divided by 2. 10 minus this is Y2 is equal to 10 minus 9.583 divided by 2. This is equal to 0.417 by 2. Then Y3, this one is equal to, here this is the plastic neutral axis. So this distance is here equal to 0.417, and from this to this is equal to 110 by 2. This is 55. This is equal to 55. This is 110 by 2, 55 plus 0.417. So this is equal to 55.41 mm. This is the Y3. Then after getting the A1 Y1, A2 Y2 and A3 Y3, the plastic moment that you can find out using this equation, MP is equal to summation of Fy into Ay. MP is equal to F1 Y1 plus F2 Y2 plus F3 Y3. Then MP is equal to Fy yield stress into A1 Y1 plus A2 Y2 plus A3 Y3. Then after putting the value of A1 Y1, A2 Y2, A3 Y3, so finally you get MP is equal to 66479.17 Fy Newton mm. Then after getting the plastic moment and the yield moment, then you can find out what is the shape factor. The shape factor is equal to plastic moment divided by the yield moment. So plastic moment you know this is this, and yield moment here you know this is the yield moment, this one. Then the plastic moment divided by yield moment, this is equal to 1.801. So the shape factor of this section, the T section, is equal to 1.801. Now all are clear. what is shape factor, then how to find out the shape factor for the different reaction.